Hello, everyone, and welcome to this Connect to Learning third series. It is with great pleasure to welcome you all to this new initiative, an initiative that started in 2020 during the COVID times when we tried to, to outreach and try to help and support educators in teaching and learning. And this third series, which will be dedicated to educational neuroscience, has been made possible with the collaboration of Educational Neuroscience Hub, the Institute of Education at University College London, and the Faculty of Education. And here I would like to thank Erica and also Andy, who will be our first speaker today, that have made this possible and for accepting our invitation to share their expertise with us. I would like to remind everyone that we will be taking the attendance, and later on, I will be sharing with you a link so that you can access the link and put in the details, because as you know, you will be provided with a certificate if you attend 5 of these series of 7 webinars that we will have for you scheduled during these couple of months. I think I will leave the word to Erica to introduce and to say something about Educational Neuroscience Hub, and then to Michelle, and then Andy. Thanks.
Thank you, James. First, I'd like to thank Professor Andy Tolmie for accepting our invitation to give an overview of this insightful area. Apologies for my voice. We are aware that education in neuroscience is changing the way we think about teaching and learning by applying scientific evidence based on the human brain to teaching pedagogy. Over the past few decades, we have experienced a revolution in brain studies, gaining a better understanding of complex human behavior. And with this knowledge, we can empower teachers and parents to reach out to their children in a more holistic manner. In fact, our aim in organizing these webinars is to create a better understanding of the development of the brain within the context of teaching and learning. And more importantly, they also aim to create a bridge, a common language between science researchers and practitioners, as well as parents, enhancing evidence-based strategies. Educational neuroscience is not a cure-all for education, but it does promise to find out how we can best support all our learners. Thank you. Hope you enjoy this introduction to educational neuroscience. Michelle, on to you.
Thank you, Erica. Thank you, James. I'm going to discuss in brief the theme of today's webinar and then introduce Professor Andy. So the title of today's webinar is What is Educational Neuroscience? Educational neuroscience attempts to coordinate evidence from behavioral and neuroimaging studies in order to obtain a more complete understanding of learning processes that can then be used to specify the pedagogical approaches and educational systems that will support these most effectively. The translational nature of this objective poses challenges because of its requirement for triangulation between researchers and educational practitioners. However, educational neuroscience research in literacy, number development, and science learning illustrates the potential of the field to explain both typical and atypical learning in a coherent fashion and to identify novel pedagogical strategies that fully address individual variation in capability. In this talk, Professor Andy will aim to give a flavor of all this work. Professor Andy Tolmie is Chair of Psychology and Human Development at the UCL Institute of Education and Deputy Director of the University of London Centre for Educational Neuroscience. He is a developmental psychologist with long-standing interest in the neurocognitive and social factors underpinning the growth of children's conceptual representations and behavioral skills in real-world settings, particularly in the primary school age range. Most of his work has focused on educationally relevant topics and settings, with a substantial emphasis on primary school science, but also on the acquisition of road-crossing skills among children. Before I give the word to Professor Andy Tolmie, I remind you what James has told you in the very beginning. We're going to send a link so that you can register your attendance for this webinar, because we would then need it for your certification. And with that, and without further ado, Professor Tolmie, the floor is yours.
Thank you so much to James, Michelle, and Erica for the introduction, and also for inviting me to do this first session for this particular series. Great pleasure to be here and to do that. So I'm going to just really not assume a great deal of prior knowledge about what educational neuroscience is, and try and take you through some of the kind of basics to give you a flavour of what we're talking about here. And then over the successive sessions that are will be taken by other people, and hopefully with less technical hitches, some of this will be expanded upon in rather more detail. So that's the kind of idea, is that this is a kind of starter really to kind of give you a flavour of things, and then this will be picked up a little bit more subsequently. And what I want to do is really just kind of take you through the answer to this question, what is educational neuroscience, by addressing that in three different dimensions of that, which I think are important. So the first is why educational neuroscience, why should we be interested in that? Then more substantively what it is, and then finally some thoughts about how educational neuroscience actually happens, how we do that kind of work, and all three of those things are important. So that's the basic shape of things. Next slide, James. So why educational neuroscience first? Next slide. So you probably recognize some of the kind of the images on this particular slide, in particular perhaps the image on the left-hand side, especially given the COVID pandemic and the role of the World Health Organization in trying to help different countries, populations manage that. And of course, the WHO has had a long-standing involvement in disease management and other aspects of public health in many different cases, many different countries. And one example of that is the information provided in African context for potential Ebola victims. And it's really very simple, straightforward information, but it's based crucially on evidence. And it's that link between evidence and practice that's really the kind of key starting point for thinking about educational neuroscience. Next slide. So that whole kind of idea of evidence-based practice has been established for a long period of time in medicine and public health. You certainly wouldn't want to go to any kind of medical practitioner who wasn't basing what they were doing on evidence and making best available use of that evidence as well. And similarly, in many public health contexts, that is also the case, that the decision making about provision is made on the basis of clear evidence, clear substantive research about work, about particular issues and how to manage them. It's curious in a sense that education has not embraced evidence-based practice in the same kind of way, though it has begun to do so, I think, increasingly more over the last 15, 20 years or so, in some countries rather more than others. And it's certainly been argued that the application in education of evidence-based practice is key to professionalization of teaching. It's a marker of successful nations within the PISA International Survey of Educational Attainment. And it's also been argued to be likely to be central to achieving national, social, and economic objectives. So basically, there's a kind of fundamental strand here of work that suggests that evidence-based practice in education should be something that we're pursuing. And it's really that underpins the whole idea of educational neuroscience. Next slide. Application of neuroscience to learning is not the only strand of relevant evidence here. I think it's important to note that. So when we're talking about evidence-based practice in education, there are plenty of other kinds of sources of evidence that we should be paying attention to. And certainly there's a very strong literature on school leadership, for instance, and the roles that kind of organizational structures within schools play in creative, effective learning environments. And certainly I wouldn't want to suggest that literature base, that evidence base is any less important. But I think the application of neuroscience, educational neuroscience in the context of education is particularly important because it's about learning processes, and that, of course, is central to the whole process of conducting education. Learning is absolutely kind of fundamental to how education is actually achieved. And then if you take that as being kind of understood, that learning is a core process, that we need to understand learning in greater degree to set up evidence-based practice that's related to that, then we have to take into account that learning depends on a physical system, the brain, of course. Those basic processes long predate human culture and any kind of explicit knowledge, and that there is a complex interface, if you like, between that kind of culturally invented understanding and the basic functions of neural systems. And we need to try to understand how these things work together. So basically what we're trying to do is to understand that interface between the physical system, the brain, and the kinds of things that we want learners to engage in schools to actually kind of come to grips with, trying to understand how those systems interface with each other, if you like, and how deliberate understanding, deliberate thought, deliberate cognition can arise as a part of that. And that's complicated because there's a wide range of evidence that's relevant to that. Certainly evidence from developmental psychology, neurocognitive, social, cultural, evolutionary, genetic. I've tried to capture a little of this on the next slide, which shows, that basically the very simple notion that individual learning is affected by a large number of different dimensions. So things which are social in origin, things which are to do with the individual development of the child, but physical development as well as psychological development, and also the kind of genetic makeup, hormonal background, and the evolutionary perspective as well. So there's a lot of complexity involved in there, potentially, in trying to understand these things. Next slide. And what we're trying to do really in both educational psychology and educational neuroscience, and I see those as being very kind of close partners with each other, is to try to set up a complex fusion of these different strands of understanding and try to develop a full model, if you like, of how brain function is affects and is affected by typical and atypical learning. So it's about trying to understand how these things interact with each other. That's the kind of basic idea here, and that isn't to kind of adopt any perspective that says it's brain function that matters and that's all it is. On the contrary, we see all these different dimensions as being crucial, and we need to think about how they interact with each other. So the emerging framework that underpins educational neuroscience, I think, sees the learner as not meaning to kind of be denigratory by it, but as a system, if you like, which operates at neural, at cognitive, and at social levels. And what we need to try to do then is try to understand how this system, to map that system, how interactions between these different levels actually play out, and how that leads to individual variation. And then onward from there to try to translate that into practice to create a useful evidence base which can help specify the pedagogies, the systems to support effective learning. So in many senses, I think educational neuroscience is best seen as a kind of engineering science. It's about taking some fundamental understandings from different dimensions about how learning actually proceeds, and then thinking about how we engineer the consequences that we see as being socially desirable on the basis of that understanding. So it's an extension of basic science into application. It's important to see it in that kind of way. Okay, next slide. So turning more substantively, having given you that kind of flavour of why this might actually matter to what educational neuroscience actually is, let's go into a little bit more detail about some of this. Though, of course, as I say, I can only really give you an overview and a flavour of some of this as far as today is concerned, and we'll pick up on this in more detail in subsequent sessions. Next slide. So there are various different things that we need to try to understand in order to be able to carry out this kind of process of thinking about how these different systems fit with each other, how they interact with each other at different levels. And so there is certainly kind of important understanding that has been around for a longer period of time. I think about the anatomical structure of the brain and how that relates to different aspects of behavior or function. And in particular, when we're thinking about issues to do with learning, we're thinking in particular about the cortex, the neocortex, and the frontal lobe in particular of the brain, which is really kind of responsible for much of the kind of higher level cognition that we're interested in. But of course, all these other systems play into that as well, in terms of underpinning basic kinds of functions. So certainly brain anatomy is something that we need to understand perhaps a little bit about, and also to think about how that might actually how these different aspects of anatomy might actually underpin certain types of learning process. Next slide. We're also interested in particular, though, in live function, trying to capture that. So in the past, it was really only possible to study brain function by in two ways. One, by kind of looking at the anatomy in people who were no longer alive, or otherwise looking at the kind of behavioural consequences for those who had suffered some form of brain injury. What technological developments over the last 20, 30 years have allowed us to do is to capture, as in live events, the kinds of activity that's going on within the brain as it's actually happening. So this is where brain imaging techniques come in, and they provide us with important type of understanding both about neural structure but also ongoing activity. And I'm not really going to say very much about this. People will talk perhaps about different sources of evidence in the context of specific areas of work in subsequent sessions, but there is a kind of quite an armory now of different things that we can actually use in order to do this. So electroencephalograms in event-related potentials enable us to study the electrical activity in the brain in response to specific types of external stimuli, and that can tell us a lot about how the brain is actually responding. Magnetic resonance imaging provides us with a picture of literally a picture of the structure of the brain and the connectivity between different aspects of it. Functional magnetic resonance imaging provides us with a map of actual activity in the brain as it's actually happening over a period of time at least. And then there are techniques, those involve perhaps lab-based machinery, but near-infrared spectroscopy provides us with an opportunity to look at also changes in ongoing brain function, but in using technology that is perhaps more amenable to everyday environments. And then there are also a range of techniques involving providing actual stimulation of the brain in order to actually see what happens as a result of that. So there's a large battery of techniques that enable us to understand something about how brain functioning is actually occurring in response to specific events in particular contexts. What we're typically doing when we're engaging in this kind of approach is looking to coordinate data from those kinds of dimensions with behavioural measurements. So what we're looking to do is see effectively how brain activity relates to behavioural activity and to try to understand some of the connections of those. And that really, that connection, being able to understand something about how brain functions is supporting and creating behavioural activity, especially in the context of learning, that gives us new insights into a range of issues that probably we didn't really have before. And that's the kind of thing that educational neuroscience is beginning to be able to do in fairly systematic fashion. Next slide. So one thing that we've tried to do particularly, I think, is to try and get the right kinds of models of how the brain is developing and how it's impacting learning processes, and how learning processes also affect the structure of the brain in turn. This isn't a one-way street. There's different directions of travel here. So some basic kind of ideas are the large-scale anatomical function structures within the brain typically develop prenatally, so that those are there ready for the infant when it's born to start making use of. But there is much that happens subsequently, and it's really, learning is primarily about creating the microstructure that actually creates new connections, enables us to understand more, to build understanding over time. And that's very much to do with the kind of activation of the brain during ongoing experiences. And there's an old adage here about what fires together wires together. So basically you encourage different sets of neurons to fire at the same time by stimulating them simultaneously, then that creates a connection that can then be used subsequently to recreate aspects of that experience and build on that in terms of a kind of knowledge, if you like, of what's happened. And this isn't a one-off static process. This changes over the lifetime The cortical structure in particular is characterized by what we call plasticity right the way across the lifespan. It continues to show change, to adapt, etc., etc., in various kinds of ways. There's a kind of tuning, if you like, by creating new connections and by getting rid of old connections, pruning away connections that are no longer particularly useful. So it's about a build up over a long period of time, really, of these different connectivities and the sophistication that can come from that. And then basically the consequences of learning, the behaviors that we're interested in that sense, are delivered by networks that involve multiple brain regions. So it's about, if you like, whole brain activity in many senses when we're talking about the consequences of learning, recall and learning, engaging in activity that draws on things we know already. There has been a kind of common thought from computer engineering that the brain operates in terms of kind of modules. So you have a kind of module for thinking about logic, for instance, or something of that kind. I think the best take on this is that the brain does not actually build the modules in that kind of way, or at least ways not over any, if they're not there to start off with, they may emerge over a long period of time, but certainly there is no kind of obvious modular structure to the brain and how it operates outside of some basic kind of anatomical functions. We'll say a little bit more about that as we go through. And also a notion that people have had previously, that there are critical periods in development and learning when you have to actually engage in certain types of learning, otherwise they won't happen. That is almost certainly wrong as well, that there are perhaps periods when certain types of learning, sensitivity to language perhaps is best in the earlier years of life. But while there are sensitive periods when learning can happen more readily, there are no periods, as far as we're aware, where learning of a particular type can no longer actually happen. It's just that there are certain kind of adaptive advantages to learning being able to happen at some points rather than others. So this is kind of giving you something, a kind of flavour of how educational neuroscience might have changed our understanding of learning, and particularly a shift away from that kind of computer-based models of what learning looks like, based on routines, based on modules, to something which is very much more literally organic in character and builds up over periods of time. And that improved knowledge has kind of key implications for both mainstream and atypical learners. I want to give you a little bit of a flavour of some of these. If any of you have expertise in these particular areas, then please don't take this as being a kind of definitive statement about these. It's not intended as such. It's really just intended to give you a kind of flavour of some of the things that we might actually be thinking about in different contexts. So next slide, please. So first of all, I'm going to look at issues relating to literacy, development of reading skills, and as a sidelight on that, dyslexia as well. Next slide. So we've built up over time a good understanding of the kind of basic processes involved in learning how to read, and this predates neuroscience work, of course, in many respects. Basically, learning to read involves mapping written language onto oral language, and there are kind of key start points that infants have as far as that's concerned. So infants have a demonstrably innate sensitivity to the sounds of language and the way we actually process that kind of information. And they become very rapidly adapted to the particular sound values that are obtained in their own particular language environment as well. So it becomes rapidly very much more sensitized to their own language context. So they're able to map sounds, and they're able to begin to decode those sounds into separated, meaningful elements that make up words, and also the way in which those words are strung together, grammatical structures which dictate what kinds of meaningful sequences of words should actually look like. So they have an innate sensitivity to that. And at the various stages in learning to read, so they can begin a kind of mapping of that kind of those written structures onto those oral structures that they're already sensitive to. So at the pre-alphabetic stage, they begin to learn to recognize whole words and to build up some understanding of how those whole words are actually associated with particular sounds and particular objects in the world. So cat, for instance, is a word that they might learn to recognize in written form and associate with its both with cats themselves and with the kind of sound cat from a fairly early stage. But they're not really doing anything to break down the way in which these sounds are being represented as yet. And then at a subsequent stage, they start to become able to do that. So at the alphabetic stage, they start to map particularly in alphabetic languages like ours, they map the kind of the phonemes, the individual sounds within language onto specific letters in order to actually begin to kind of see the connection between those. And in particular, there seems to be a stage of early sensitivity to what are called onset rhyme structures. So being able to kind of break down words into kind of smaller units, but not necessarily at the letter level yet. So cr and us, at least the word crust, for instance, and they can do that. And then they begin to see the kind of letter correspondences more, letter sound correspondences more fully. And then at the orthographic stage, that those processes of recognition become automated. They stop having to kind of sound out words in order to actually recognize them and be able to say them. They go back effectively to, in some senses, to the pre-alphabetic stage with whole word recognition, being able to recognize words and recognize what the sounds of those words are without actually having to go through the process of breaking them down into individual units. So that's the basic kind of process of learning to read in a very, very small nutshell. Centrally important to this is this awareness of phonology that I was talking about at the beginning here, and being able to kind of process sounds in accurate fashion and then bind those sounds together with their meaning, together with the written symbols, into a kind of overall structure where one can access the other without any kind of can activate in neural terms the other without any kind of specific detailed processing being necessary. That's the stage of automation. So basically sounds stimulate recognition of words, of meaning, of letters. These things are all kind of interconnected with each other. And that seems to be, in some sense, what underlies fluent reading. It has been conjectured at some points that there is a specific area of the brain, the verbal word form area, in the temporal parietal left ventral cortex, if that means anything, which might be responsible for that. That seems to be perhaps rather more questionable now, but that kind of binding is definitely something that seems to be a crucial part of the process of learning to read. Next slide. And then when we come on to thinking about dyslexia, really the problem seems to lie, at least in part, in an extreme form of deficit in that phonological awareness, and also what we call metaphonological awareness, which is actually being able to manipulate sounds and to think about how sounds relate to each other. That seems to be something which is impaired, and that might lead in turn to poor connectivity within this kind of, if it is the visual word form area, but basically this area of the brain that connects orthography with sounds, with semantics, with meaning. Certainly seems to be something which is characteristic of dyslexia. And there seems to be some evidence, at least, of a kind of anomalous and unusual neurotransmitter profile. So there's something going on at that level that seems to be particularly difficult in connecting these things up. And there is also more recent work suggesting that actually this might be something to do with poor regularity detection, that it becomes difficult for those with dyslexia to actually detect regularities in effective fashion. Other people will say more about this in due course. But the other thing to note here is that it interacts with the extent of regularity in letter sounds relationships in the child's native language as well. So if you've got a language like English, which has actually quite a lot of irregularity in letter sound correspondences, we use the same letters to make different sounds, and the same sounds are often made by different configurations of letters, which is potentially very confusing. So problems with mapping those regularities seem to occur more in languages which have that irregularity, whereas in a language like Italian or Spanish, which is very, very regular. Those problems seem to occur less often. So the kind of underlying take on this, I suppose, is that, to give you a flavour of where we've got to, is that this indicates that a key dimension is really some kind of neural sensitivity to complexity in the mapping of words onto sounds, and the ability to form stable representation schemas, is the term for those that enable those to be recalled subsequently. And so there seems to be problems in building up that sense of regularity. And one form of remediation that's been suggested is deliberate practice of some of these kind of sound letter correspondences over time in order to actually build up stronger representations of those regularities. And we certainly also now have the ability to detect at an early stage children at risk of these kinds of problems through potential neural markers and also potential genetic markers as well. So we've got beginning to build up quite a sophisticated model of both the reading process, learning to read, and also some of the things that can go wrong with that. Next slide. So I want to also say a little bit about development of number and problems with that, what we call dyscalculia. Next slide. So basically, we have some similar ideas to those that I've talked about in the context of learning to read. So evidence says that we have actually innate number recognition systems. So we have a small exact recognition system that enables us to recognize 1, 2, 3, possibly even 4 or even 5 objects as having that number without actually having to deliberately count them. A process that we call subitization. Think about the numbers on a dice, the face of a dice, for instance, or on a playing card. These are patterns that we're very used to seeing, and we don't have to count the numbers there. We just simply recognize them as being what they are. So that's one kind of system. And the other is a larger relative system that enables us to from birth to be able to distinguish between say, something which is twice as much as another. So 32 items versus 16, we can readily tell the difference between these. And it also seems to be the case that many other species of animal have these innate recognition systems as well. And you can see there might be an evolutionary advantage in, for instance, knowing which tree to forage from by making use of this kind of number processing systems, innate systems. Now, it's been argued that those systems then provide a basis for counting skills. It's not to say that this is the same as the kind of mapping that's involved in learning to read. So it's not like the simple correspondence of letters to sounds. This involves a number of other principles as well that have to be mapped on if it is a matter of mapping onto these systems. So there are lots of principles involved in counting, that we have to understand things that, you only count something once, the one-to-one principle, the stable order, so it doesn't, the numbers themselves that we use have a fixed order and we don't vary that order. It doesn't matter what order you count things in, though, because if the number is, if the number of items is static, then the end result will be the total. And that's also to do with the principle of cardinality, understanding that final count is actually the total number of things we have. So there's some behavioural aspects about learning to count, if you like, and some of the principles are involved in that go beyond the kinds of things that would suggest simple mapping. And also we know that there is a kind of potentially crucial moment at the stage of learning number symbols as well, and being able to understand how those number symbols relate to specific types of specific numbers in the spoken sense and in the sense of things that we can actually look at and count. So there is certainly a kind of key stage for being able to do that symbolic mapping. And then there are lots of other higher order skills involved in doing arithmetic. This before we even get on to things like mathematics and various complex procedures within that, but just simply understanding basic number facts. If you multiply something by 10, then in our system that simply means you add a 0 onto the number that you're multiplying by 10. And use of those number facts to develop strategies for actually carrying out calculations and for remembering calculations as well. So all of these things seem to be particularly important in developing refined arithmetical and then subsequently mathematical ability. And there doesn't seem to be any very consistent order in skill emergence. So in many respects, learning arithmetic, learning mathematics seems to be a more complex process than learning how to read, because of these the greater number of processes involved and the apparent kind of relative kind of independence of many aspects of these skills. They all build up into a composite picture, but they seem not to depend on each other in terms of learning. They have to be kind of built up as a composite, if you like. And there's a lot of individual variation as well. Next slide. So developmental dyscalculia is a condition that seems to affect the ability to do this kind of processing, and it seems to lie particularly in the difficulties with ability to enumerate sets, to perceive number in that kind of sense that I was talking about at first, about the kind of innate number recognition systems. And the argument has been that that makes it difficult to create a meaningful structure for learning arithmetic. And there does seem to be some association between that kind of difficulty and certain kinds of functional abnormalities in aspects in regions of the brain that seem to be specialized for enumeration, though there is a kind of debate about whether that is really consistently true, and how far there is a kind of clear picture there. People have tried to build up interventions along similar lines to the ones I talked about for dyslexia, using specialized software to create this kind of stronger number sense. But as far as current evidence is concerned, there seem to be other things which actually seem to be at least as important, possibly more important. So being able to attend to the right information they want to actually look for, ability to use what we call working memory, the ability to actually retain and manipulate information, number facts, again, that mapping onto symbols, all of these things seem to be important. So in terms of provision for improving mathematical, arithmetical learning, we're perhaps somewhat further away from having kind of very decided answers than we are in the context of dyslexia. And we perhaps need a wider suite of strategies as yet to be specified. But we have developing understanding of something of the complexities of learning number as part of this, and that's come again from this kind of work in educational neuroscience. Next slide, please. So finally, I just want to say a little bit about science learning, which is, as Michelle said at the outset, is more my own particular area of specialization. Next slide. So there are various complex ways that we can think about science, but certainly a kind of key idea that is really very central to learning in science is this idea of building up concepts of things, ideas about causal processes that provide the basis then for scientific testing. So for instance, we might be talking about concept of floating and what types of objects float, what kinds of properties need to be present for an object to float as opposed to sink. And we build up over time concepts about what these kinds of characteristics might be, and also what the process is that's involved in objects floating, the interaction between fluid and solid, or objects sinking, similar kind of interaction but with a different kind of outcome. So these concepts seem to be really kind of central to learning in science, learning explicit science anyway, because those then provide the foundation for development of scientific theories. Now, again, we seem to have evidence that infants have an innate sensitivity to causal information, so they are able to detect from a very early stage, certainly within a few months of birth, able to detect causal regularities. So one event regularly following another is noted by them and is seen demonstrably in some sense as being a causal connection. They see this as being, one thing literally following another. And by 24 months, they can actually accurately anticipate what happens when you put combinations of causes together and project an outcome that might actually follow from that. So there is this kind of, again, a kind of innate sensitivity to things, which seems to be important for providing a foundation for understanding. But again, we have this kind of problem that this is based on an implicit sensitivity to these things, and it's not about, this isn't about something which is automatically verbally accessible. and therefore open to analysis. And indeed, verbal concepts about scientific processes seem to be acquired primarily via conversation rather than by observation. And as a consequence, EEG studies looking at electrical activity in the brain with adults show that, that there are separate neural activations for accurate implicit perceptions and inaccurate explicit concepts. So basically, if you show people an erroneous event, but one that they commonly think is correct, then they will still think it's correct. And yet some aspect of brain function indicates that actually at a perceptual level, they know that it's not correct. So we seem to have two separate things going on, and failure to integrate this kind of innate perceptions with explicit concepts seems to be something which is commonplace. Next slide. So a crucial educational step then, if we take that as being the case, is to actually encourage accurate mapping of explicit concepts onto those implicit perceptions. And that seems to be kind of something which is related particularly to working memory and executive function, which is linked to activity in the frontal cortex in particular. And we know that those systems are relatively immature, are more difficult for children to manipulate properly until after the age of 10 or so. So those seem to be potentially kind of challenges into integration, might make things more difficult. And we also know from more recent research that there seem to be kind of key attentional abilities that are involved here as well. Being able to pick up the right kind of information and then encode that in language seems to be kind of a crucial aspect of learning science. So noticing exactly how, for instance, a stone sinks in water differently from how a grape sinks in water. There's a difference in the rate at which the objects sink, and that's telling us something about the kind of processes involved. Being able to attend to that information and make use of that information explicitly seems to be a key part in creating this coordination between perceptual information and conceptual understanding, which suggests that actually there is a kind of importance then as far as teaching is concerned in creating that kind of better attention, focusing on that, and then helping develop explicit vocabulary to capitalize on that. And there's also a lot of work on collaborative group work in science that that involves exactly this kind of coordination of implicit perceptions, encoding those, making them explicit for other people. That seems to produce robust improvements in conceptual understanding. So again, we have some clues from the education neuroscience for what the kind of appropriate strategies might actually be. Okay, next slide. Thank you. Briefly then, to finish off, something about having given you a flavour of what we're actually talking about. The thing I want to finish with just briefly is how we see educational neuroscience growing and what is actually involved in that. Next slide. So we have some problems at the moment. So I've given you a flavour of some of the kind of relevant research, but it would have to say that at the moment it's relatively fragmented and unevenly developed. So we know a lot more about literacy development than we know about maths development, maths learning. We know a lot more about maths than we know about science. So there's a kind of, and then, you know, when it comes to other areas of the curriculum, we know even less about those. So it's very unevenly developed. And we need a coordinated program, more coordinated program that helps us see common messages really across different areas of work. We also need to make sure that we're thinking about this, as I've kind of said before, really on not just in terms of neuroscience, but linking that to behavioural work. So bringing those two together. And indeed, much of what we understand about effective interventions at the moment is based not on the neuroscience, but rather on the behavioural work that's been done to show what types of support for learning are effective. But we begin to be able to understand better why some of these things actually work. Bringing in the neuroscience that tells us more about that, and so you know, we're able to develop better understanding that may in time lead to further types of effective intervention as well. And that's the kind of goal. The evidence today suggests that we, perhaps a key point, that we need to look for different kinds of approaches to learning in different areas. as I perhaps indicated, going through just giving you a flavour of work on literacy, number and science. There seem to be really different things involved in learning in each of these areas. So there's a few general principles that we can actually point at. Symbol mapping is perhaps one of the kind of few things that is common across these areas. So basically, we need to be thinking about this probably in terms of support for different areas of learning that involve different strategies, and that's obviously got key implications for teaching practice. But above all, what we need to do is to build better connections between different communities, if this kind of connection between research and practice is actually what's going to become a reality. And that's very much how public health science grew. It was a combination of people working in the public arena with biologists, etc., to develop effective models. And it's really perhaps gives us an idea about what educational neuroscience needs to look like. It's about that building of connections between practitioners and researchers. Next slide. And so really that, entails researchers from different backgrounds working together, but also creation of this kind of wider community involving teachers, teacher trainers, educational psychologists, etc., professionals in that sense, but also engaging with policymakers and policy shapers to ensure that this is seen as a valuable exercise and one that we should be actually engaging in. And so it's that gives you a flavour of how we try to carry out educational neuroscience work and that translational work that I've been talking about. And that's why sessions like today really are seen by us as being incredibly important. And we have these centres, our own Centre for Educational Neuroscience in London, Educational Neuroscience Hub at the University of Malta, provide a kind of focus for this activity. But we have an onward goal of trying to build this into a much bigger network, a global network, if we can make it so. With the help of UNESCO, and we're certainly engaged with much dialogue with them at the moment to try to bring them on board in the same way as the World Health Organization have done this for public health science. Thank you, that's me. Sorry for the pause at the start with the technical problems, so we've not got so much time left for questions, but hopefully some.
We have a few questions, Andy. So,
thank you.
First question is, can you recommend a book to read more about learning from the perspective of education and neuroscience?
It depends on what level you want to actually take that. I mean, there are two excellent textbooks that I have been involved in that will provide you with detailed information. So one was the book Educational Neuroscience that was edited by Denis Marichal, Brian Butterworth and myself in 2013, but there's a more recent text edited by Michael Thomas, Eros Dumontai and Denis Marichal again, called Educational Neuroscience Across the Lifespan, if I remember correctly. So that will give you detailed information, but that may be beyond where you want to be. If you want to have a kind of good introduction to this, on the Centre for Educational Neuroscience website, and Erica can give you the link for that. There is a lovely resource called How the Brain Works that was developed by Michael Thomas, with user-friendly graphics and nice cartoons and things like that, which you may find a good start point. And I think that's a good place to begin.
Another question is, do you know if there's research about the effects of sensory activities provided in school settings to the learning of students exposed to those activities from an educational neuroscience perspective?
Well, sensory activity is really crucial, I think, in all aspects of learning. And yes, well, there's a lot that could be said about that. I mean, at the moment, colleagues of mine and myself within our department at the Institute of Education are very much concerned with relationships between cognitive development learning and motor development. And we think that there is actually a very kind of key role for sensory motor development in learning. And basically, the idea is that much of the kind of fundamental concepts that we're building up about the world, but also the kind of basic cognitive systems that we're using when we're engaging in problem solving, thinking about particular tasks that we need to engage in, that that those skills are first acquired in the context of supporting manipulative ability, motor skill of one kind or another. And so that kind of sensory input seems to be really kind of crucial there. That's a big question, though, requires a lot of detailed answer. I think there is a key role generally. I think the way in which that actually pans out is probably different depending on different areas of learning and what it is we're trying to achieve. So that, you know, would need to come down to more specifics. And maybe some of the subsequent sessions might actually touch on this in a bit more detail.
One last question, because we're near the end of the webinar.
Yeah.
What do you think we need to be doing in the next 5 to 10 years in order to realize the potential and impact of education in neuroscience?
There are no small questions here. There are no small questions, are there? What do we need to be doing? Well, we need to be doing a lot of what we have been doing already, but doing it more and more effectively, I think. So the dialogue between teachers, parents and researchers is really a crucial part of this, so that we build up some kind of shared understanding of what it is we're talking about and how to focus on this. And that's not to expect teachers and parents to become, you know, experts in the research evidence, but to understand something of the kind of key pointers. So we're coming at this from a kind of common perspective. I think that's one aspect of it. And also that, you know, it's teachers and parents telling us what things we should be researching, because, you know, we have our, you know, researchers have their own particular agendas and things they're interested in. But if we want this to be effective in terms of translation, then we have to understand better what problems are faced by educators and how we can actually address those by collecting the right kind of evidence. I think that's the crucial step. And beyond that, I think, you know, trying to internationalize this as far as we possibly can. I mean, there are obviously, you know, particular cultural variations in much of how this actually operates, and not least in terms of how educational systems run. But a lot of the principles that we're talking about, I think, probably fundamentally are universal or near universal. And so I think, you know, it's important that we actually make this evidence base available, not just to people in the developed world, but to people in the global south, in particular in Africa as well. So something else what I was hinting at the end there, we're trying to build up this more kind of global network that will take this translational work into places which have not had really very much connection with it so far. So there is a kind of, you know, genuine possibility of a more level playing field internationally, in the same way as, you know, strides have been made in terms of health practice to promote that. And we need to try to do the same for education as well. UNESCO are on the case. I think they're a good organisation. We need to be working with them.
Thank you, Andy, James and Michelle. On to you.
Thank you all. Thank you for your interest and attention, everyone. And apologies again for that delay at the start.
Yes, thank you, Andy. A very insightful presentation, a lot to think about, you know, and to discuss further. I would like to invite, I've shared in the chat a link to register for next week's webinar, which will focus on memory. And this webinar will be, our speaker will be Dr. Rebecca Gordon. So we invite you to register and be with us next week. Michelle, I'm not sure whether you'd like to add anything.
Just a quick thank you. Always very insightful what Professor Andy has shared with us, and I always manage to go out of this webinar with more questions and intriguing thoughts and surprises. You know, there are many misconceptions, I must say, regarding neuroscience, but it's good that we question and we deconstruct what you presented us with. A lot of food for thought.
So thanks again. Thank you, Andy.
Thank you, Andy.
Michelle. Thanks, Erica. And thanks, everyone. Have a nice evening. Thank you.